All right. Do you remember that when we first talked about the derivative, you had one notch homework that you had to find the derivative of a function using the definition of a derivative. And it was kind of painful. Limit is h goes to 0, f of x plus h minus f of x over h. Got it. That's kind of what today's homework is. Today you're going to learn to do something maybe a little painful so that you can truly appreciate what a definite integral is tomorrow. Today we're dealing with area, and the first thing we need to talk about is this summation notation or sigma notation on page 290. There's a symbol we haven't used before in here. You may have seen it somewhere else. The sum of n terms, a sub n, or a sub 1, a sub 2, a sub 3, all the way up to a sub n, is written with that notation. That's sigma. The sum, you read that the sum from I equals 1 to n of a sub I. And what this notation is telling you to do is put 1 in the place of I, and then put 2 in the place of I, and then put 3 in the place of I, all the way up to put n in the place of I. I is called your index of summation. That's the variable that's increasing from 1 to n. A sub I is called the ith term of the sum. And the upper and lower bounds of summation are the 1 and the n. N's the lower bound of summation, and n's the upper bound of summation. So we're going to use some summation notation, sigma notation, and some formulas for finding sums, to find some sums, and then tomorrow we're going to find a whole lot easier way to find area. But all of today's leading up to being able to find area using sigma notation. All right, so in your notes, I didn't want you to have to write all these down, so I just typed them, put them in the notes for you, or copied it from the book, put it in the notes for you. Sorry. Number 2 says find the sum from k equals 3 to 6 of k times k minus 2. Now here, our index of summation isn't I. For some reason, they're using k's. That doesn't matter. That's arbitrary. But that means in this formula, or in this function, k times k minus 2, first let k be 3, then let k be 4, then let k be 5, and then let k be 6, and sum up those 4 terms. So when we let k be 3, because that's our lower bound of summation, we would have 3 times 3 minus 2. And when we let k be 4, we would have 4 times 4 minus 2. When we let k be 5, we'd have 5 times 5 minus 2. And when we let k be 6, we would have 6 times 6 minus 2. So we just want to evaluate the sum. This problem is just about making sure that you understand what that notation means. So this would be 3 times 1 is 3, 4 times 2 is 8, 5 times 3 is 15, and 6 times 4 is 24. I think that all adds up to 50. So the sum of k times k minus 2 from k equals 3 to k equals 6 is 50. See if you can get number 4 real quick. Our index of summation is j. We're supposed to sum up 1 over j from j equals 3 to j equals 5. When j equals 3, what fraction do you have? 1/3. And when j equals 4, you have 1/4. And when j equals 5, you have 1/5. Get a common denominator, add those all up, get 47/60. I don't know if it was the Sudafed plus the ibuprofen plus the Robitussin plus some other various pills in the cabinet this morning. But when I looked at 1/3 plus 1/4 plus 1/5 and saw that gave me 47/60, I just thought, cool. I'll get all those ones, give me a 47. You have to be on lots of Robitussin. All right. I love y'all, or I would still be home in bed. Let's look at 7 through 12 say, use sigma notation to write the sum. So we're given some series of things that are added together. We want to find what sigma notation would give us that series. That's supposed to be the sum of something, and we just have to figure out what the something is. What's changing in each one of those terms? Second term of the denominator, and you said that like a math teacher. Second term of the denominator started 1 plus 1, but then became 1 plus 2, and then became 1 plus 3, all the way up to 1 plus 15. So where do you think our, if we're using, it doesn't tell us what variable to use, but if we use I for our index of summation, we're going to have I equal something up to something else. What do you think the something else is? Yeah. We're summing up some stuff from I equals 1 to 15. Now, what is it that we're summing up? 5 over 1 plus I. And then just double check that. If I let I equals 1, would I have the first term? Yeah, if I let I equals 2, would I have the second term? And I equals 3, I'd have the third term, all the way up to I equals 15, and I'd have the last term. So we found the sigma notation that represents that series. One more, what about number 10? What's changing in number 10? The numerator, the first term inside brackets is staying the same. The denominator of the fraction that's being squared stays the same. It's the numerator that's changing. And that numerator begins at 1 and goes up to 4. So that looks like a sum of something from I equals 1 to I equals 4. How would you write what that something is that's being summed up? 1 plus, instead of 1 over 4, that 1 is changing, so I over 4 squared. That is minus. I don't know how it got to be plus. No, it gets way more fun than this. We're just understanding the notation right now. Glenn? No, they didn't tell us what to use. Probably the most common index of summations, I, but if you use a J or a K, absolutely fine. Yeah, that's kind of misleading. We try in math not to use any symbol for two different meanings, and every once in a while there is a symbol that means two different things, like sometimes parentheses mean multiply, sometimes parentheses don't mean multiply. That I has nothing to do with an imaginary number at all. It's just an index of summation. And that's a very bad minus in between those. All right. We have some summation formulas on page 291. I was looking to see if there was a little blurb about Mr. Gauss in here. I don't see Mr. Gauss's name anywhere. I can't even think of his first name right this minute. But as punishment in elementary school, I think it's Frederick Gauss, he apparently was a very bright kid, and as very bright kids are, sometimes he acts out and is unruly, and so the teacher said, find the sum of the first 100 numbers, expecting Gauss to sit down and add 1 plus 2 plus 3 plus 4 plus 5. Well, Gauss almost immediately came back to the desk and said what the answer was, and kind of freaked the teacher out, which it would freak me out. And teacher said, how did you figure that out so fast? And Gauss said, well, the sum of n digits is just n times n plus 1 divided by 2. Okay.
Is he with elementary school?
Yes, he was in elementary school. I think you'll have to Google that story. You'll have to Google that story and see how spot on I am. But his name Gauss, and he discovered this summation formula right here when he was a baby, practically. The sum of the first n digits. There's a formula, so you don't have to sit down. If you want to add up the first 100 digits, you can just add up 100 times 100 plus 1 and divide by 2, and that'll give you the sum of the first 100 digits. If you want to sum up a whole bunch of squares, you want to sum up the first 40 perfect squares, you can just multiply 40 times 41 times 81 and divide by 6. That'll give you the sum of the first 40 perfect squares. And here's the formula for the first 40 perfect cubes. You don't have to memorize those. You're not going to need them on the test. But we're just this is all leading up to something. And hey, I skipped that first one. If you add 15 to itself 7 times, what do you get? 7 times 15. If you add 47 to itself 20 times, you get 47 times 20. If you add C to itself n times, you get C times n. So the next problems in the notes say, use the properties of summation to evaluate the sum. And let me just say that for these two, all we're going to need is the sum of I equals 1 to n of a constant is the constant times n. Where's that written? Right there. And the sum from I equals 1 to n of I is n times n plus 1 over 2. And then the sum of the first few perfect squares from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 divided by 6. So what about number 16? If we wanted to do number 16 the same way that we did number 2 and number 4, we would have to let I be 1, and then let I be 2, and then let I be 3, all the way up to I equals 15. And we could certainly do that way. But if we want to be as bright as Frederick Gauss, then we can use these summation formulas. Now, if we were as bright as Frederick Gauss, we would have come up with the summation formulas. We're not that bright anymore. We just use what he's already done. Number 16, the sum from I equals 1 to 15 of 2i minus 3. One thing I didn't tell you, Theorem 5.2 says you can take sum of a binomial by taking the sum of each term. So I can split that apart into sum from I equals 1 to 15 of 2i and use this formula to figure out what that is, and then subtract the sum from I equals 1 to 15 of 3. All right, according to Gauss's formula, the sum from I equals 1 to 15 of 2 times I is 2 times whatever the summation formula is. The summation formula for I, sum of a bunch of i's, you multiply n times n plus 1. In this case, what's n? 15. So 15 times 16, and then divide by 2. That's using this formula right here. And then subtract what you get if you add up 15 threes. What do you get if you add up 15 threes? Yeah, 3 times 15 or 45. So when you simplify that, the 2's cancel. 15 times 16 is what? 160 and 80, 240? Minus 45. It's 195. That's faster than we could have let K be, what did we start with? 1? Let K be 1, let K be 2, let K be 3, let K be 4, all the way up to let K be 15. The summation formulas just helped us to do that more quickly. So grab your buddy and see if you can figure out number 18. What is n here? 10. So to sum up a bunch of I squares, we would need to use this formula where n is 10. 10 times 11 times 21 divided by 6. That's the sum from I equals 1 to 10 of I squared. And then if I subtracted from that, adding 1 to itself 10 times, anybody grab a calculator? Yeah? I got 375. All right. So that is only easy because we have those 3 formulas. If we had something that I didn't have a formula for, it would take a lot longer. I could still do it, but I'd have to let I be 1, I be 2, I be 3, all the way up to I equals 10. The only way this could possibly get more fun is if we threw the limit as n goes to infinity on there.
Maybe this is why you have a goal.
Could be.
Yeah.
Number 40. Yes, I'm one in my pocket. Just in case.
Maybe we all need road testing.
All right, so we want to find a formula for the sum from I equals 1 to n of 2I over n times 2n. And then we want to find the limit as n goes to infinity. I think I can. We're just going to keep up with that in every step so that we don't lose it. And we want the sum from I equals 1 to n. What could I do to simplify that? I could multiply them, 4I over n squared. And don't forget that because n is some fixed number, I don't know what it is, but it's not a variable, it's not changing, it's my upper limit of summation. So really this 4 over n squared would just be a constant if I knew what n was. This is just 4 over n squared times summing up a whole bunch of i's. I know how to sum up a whole bunch of i's. Do I still need the summation notation in this step? Not if I'm about to use the formula for summing up a bunch of i's. I just need to think one thing. Something's bugging me. Let me think what it is real quick. 4 over n squared times the sum of a bunch of i's. Yeah, I don't need the summation notation right here because I'm about to use the formula for summing up a bunch of i's. This is 4 over n squared times, what's the sum of a bunch of i's from I equals 1 to n? We have that. We have a formula for that. Oh. I like that, Chase. Chase is going, that makes sense. And then let's keep on working on what's inside parentheses. What does this simplify to? Well, the 2 would go into the 4 2 times, and the n, one of those n's would cancel out one of those n's. So I just have 2 times n plus 1, or I could write it 2n plus 2 over n. And I want the limit of that as n goes to infinity. Think about if n was a billion, then 2 times a billion, this 2 wouldn't make much difference by the time you said 2 times a billion. This would be 2 billion and 2 over 2 billion. No, 2 billion and 2 over 1 billion. That's just 2. That's the theorem on horizontal asymptotes right there. The limit as n goes to infinity of a rational expression, if the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote is just the ratio of the leading coefficients. So that limit is 2. What does any of this have to do with area? Well, another genius, Archimedes. I know. Archimedes lived before there were formulas for finding areas of geometric shapes. Archimedes was trying to find the area of a circle, for example. There was no a equals pi r squared before Archimedes. There was a equals pi r squared after Archimedes. And Archimedes said, I don't know how to find the area of a circle, but I know how to find the area of a triangle. But I divide a circle up into a bunch of triangles? Well, not exactly, but kind of, sort of. This is dividing a circle up into 1, 2, 3, 4, 5, 6 triangles. And 6 triangles are inscribed, they're inside the circle, and then 6 triangles are circumscribed outside the triangle. And Archimedes says, if I just take the sum of the 6 inscribed triangles and then the sum of the 6 circumscribed triangles and average those two, then I should be close to the area of that circle. And then he said, hey, the more triangles I use, the closer the area will be to what we know the area of the circle ought to be. Actually, he didn't know it at the time, but he says, the more triangles I use, the better approximation the sum of the inscribed triangles and the sum of the, the average or the sum of the inscribed triangles and the sum of the circumscribed triangles will be to an approximation of the area of that circle. If we took the same circle and divided it up into 40 triangles, then that would be even a better approximation of the area of the circle. So that, believe it or not, is called the method of exhaustion. Can you see why it's called the method of exhaustion?
Yeah.
What's that thing in calculus way before Archimedes, or way after Archimedes? What's the symbol for using more and more triangles without bounds? That sounds like a limit, doesn't it? That sounds like the limit as the number of triangles goes to 0. Not goes to 0, goes to infinity. The limit as the number of triangles goes to infinity. So that was way before video games. Everything amazing in the world was invented before video games. Nothing amazing's been invented since Pac-Man. Because people are too busy playing Pac-Man. Show you one other thing in the book, and then we're going to flip that handout over and talk about what I have on the back side. If you think way back to about the first day of class when I showed you that professor, was his name Professor Berger?
Yeah.
And he talked about the 2 big questions of calculus. The first big question of calculus is, how fast was I going on my bicycle at the moment I passed that stop sign? We know now that that's instantaneous velocity, and instantaneous velocity takes calculus. Average rate of change doesn't take calculus. Instantaneous velocity takes calculus. The other big question of calculus was, I think he phrased it, how do I find the area of exotic shapes, or the area under a curve? This is way after Archimedes. Somebody said, we could take any piece of a curve and divide that piece of a curve up into little rectangles. We could find the area of each rectangle, add those together, and that's close to the area of the curve. And then, like Archimedes, we'll take some inscribed rectangles and we'll take some circumscribed rectangles, and we'll find the average of this area and that area, and that's pretty close to the area under the curve. It'll be even a better approximation if we let the number of rectangles go to infinity. And that's where this came from. That's in your notes. I'm going to make this make sense. Let f be continuous and non-negative. We're going to talk about why the non-negative later, but right now let's just talk about functions that are above the x-axis on some interval from a to b. We want to find the area of the region bounded by the graph of that function. Here's some function. It's above the x-axis from A to B. We want to find the area bounded by that curve and the x-axis and the lines x equals A and x equals B. We want to find the area shaded pink right there. Then here's the formula for finding that area. That area will be the limit as n goes to infinity. Think of number of rectangles goes to infinity of the sum from I equals 1 to n of f of c sub I times delta x. Do you need some, is that okay, or you need some explanation?
Yeah.
What the heck? Well, delta x is just the width of a little rectangle. There are infinitely many rectangles in here. Delta x is just the width of one of the rectangles. F of c sub I would be the height of that rectangle. We're just summing up a bunch of heights times widths as the number of rectangles gets bigger and bigger and bigger. It makes sense that that would give us area. Using more rectangles gives us a better approximation of the area. And we're just summing up the length, this is the length, times the height of each of those rectangles. And we just did a problem that had something like that in it. So you give me a function that is above the x-axis, bounded by some intervals a to b, and I should be able to use that formula to find the area. That's what we're doing that's hard today, and it's going to be easy tomorrow. I like my sideways typing here. The limit as the number of rectangles increases without bounds of the sum from I equals 1 to n, that's adding up the area of n rectangles. The height of each rectangle times the width of each rectangle, where the width of each rectangle is b minus a divided by n. That kind of makes sense. If I got the area from a to b and I'm going to divide it up into n rectangles, I'm going to divide it into 2 rectangles, then each rectangle will be b minus a divided by 2. Would be the width of a rectangle. If I use 3 rectangles, then the width of each rectangle would be b minus a divided by 3. If I use n rectangles, the width of each rectangle will be b minus a divided by n. So that's how I'm getting the width of the rectangle. And one other thing, c sub I, some point under that curve, some x value under that curve, is the left endpoint plus I multiples of the width of the rectangle. If the width of the rectangle is 2, and I wanted to get right here, I would just add, I'd start at A, and I'd add multiples of 2 until I got right here. C sub I, f of c sub I is the height of the rectangle, and you get to c sub I by adding I multiples of the width to the left endpoint. You only have one of these in the homework. We only have time for one of them in the notes. Number 48. By the way, don't do the odds from this paper from homework. This is actually a previous edition of the book, and you wouldn't have the odd answers to check in the back of the book, so make sure you do the homework from the back of the book, not from that page, and the homework is written at the bottom of the notes. But number 48 says, use the limit process to find the area of the region bounded by y equals 3x minus 4 on the interval from 2 to 5. Let's see if we can draw the area we're trying to find. We want the area bounded by the line y equals 3x minus 4 from 2 to 5. I need to know what the endpoints of that line segment would be. At the left endpoint, y would be 2 times 6, or 2 times 3 is 6. 6 minus 4 is 2. So 2, 2 would be the left endpoint. And if I let x equal 5 to get the right endpoint, 3 times 5 is 15 minus 4 is 11. I'm just going to say way up here somewhere there's an 11. I'm trying to find the area under that line segment bounded by the x-axis and the vertical lines x equals 2 and x equals 5. That's the area I'm trying to find. Do I really need calculus to find the area? What shape is that? That's a trapezoid. How do I find area of a trapezoid? You average the short base and the tall base, and then use the width. It's the length times the width. Area of a trapezoid is the width of the trapezoid times the, actually, let me write it this way, the width times the average of the bases, base 1 plus base 2 divided by 2. In your geometry book, it may have been written with different letters, but basically that's what it is. The width of that trapezoid is what? 3. And then if I averaged the 2 plus 5, that's 3 times 7 over 2. That's 21 over 2. Have I done something?
Basically, that's the size of the trapezoid's height.
Yes. Yes. Yeah. I was supposed to say the height of the short side is 2 and the height of the tall side is 11. I'm supposed to be averaging the 2 and the 11, not the 2 and the 5. So 13 over 2. It didn't take calculus to figure out the average of that, or the area of that trapezoid is 39 over 2. I just want to show that I can get the same area using that definition that we just saw. So the definition, back of something, back of this. That area formula is the limit as n goes to infinity of the sum of infinitely many rectangles height times width, where the width is b minus a divided by the number of rectangles, and c sub I is the left endpoint plus I times the width of each rectangle. We've got to figure out what all these symbols are. We've got to figure it out in 10 minutes. What's my function? This f of c sub I, what's the function that I'm trying to find the area under? All right, so f of x equals 3x minus 4. That's the function. And what's my a and b? The 2 and 5, the endpoints. A is 2 and b equals 5. So what's the width of each rectangle if I divide infinitely many rectangles, if I inscribe infinitely many rectangles on the interval from 2 to 5? What is the width of each rectangle. 5 minus 2 over n. I don't know what n is. I'm going to find the limit as n goes to infinity. But each rectangle will be of width 3 over n. And what's this point C sub I that I'm going to use to find the height of each rectangle? Well, C sub I is A is 2, plus I times the width of each rectangle is 3 over n. So far, is there any question about how I picked out the F, the A, the B, the delta X, or the C sub I? So far, so good. All right. This definition says the area is the limit as n goes to infinity of the sum of I equals 1 to n. How do I find f of c sub I? What does that mean? If I say find f of 3, what does that mean? Put 3 in the place of x. If I say find f of hippopotamus, what does that mean? Put hippopotamus in the place of x. If I say find f of c sub I, that means take this c sub I, plop it in place of the x. Here's my c sub I. I'm going to put that in place of x. I'd have 3 times 2 plus, I'm going to call that 3i over n, just think, because I think that'll look simpler. 3 hippopotamus minus 4. That is that. And then what else is part of that stuff that's being summed up? Times delta x, which is 3 over n. All right, it kind of looks like number 40 now. It's a little bit scary, but I'm just going to clean up this stuff as much as I can and then use a summation formula if I need it, and then take the limit of that as n goes to infinity. So how much can I clean up this stuff that I'm finding the sum of? Well, cleaning up inside brackets as much as possible, I could say that's 6 plus 9i over n minus 4. That's the limit as n goes to infinity of I equals 1 to n. Inside brackets, I could just say that's 2 plus 9i over n times 3 over n. That's the limit as n goes to infinity of the sum from I equals 1 to n of, I distribute the 3 over n, I have 6 over n plus 27i over n squared. Is that right so far?
Now that I've cleaned up what's inside parentheses as much as I can, it may be time to use one of my summation formulas. I'm taking the sum of I equals 1 to n of 6 over n plus 27i over n squared. This is just a constant, and this term involves summing up a bunch of 27 over n squares. I have a formula for summing up I iterations of that. So I'm ready for the limit as n goes to infinity. I don't need the summation symbol anymore because I'm about to use the summation rules. The summation rule says the sum from I equals 1 to n of a constant. This is a constant. I don't know exactly what it is because I don't know what n is, but the sum of a constant is just the constant times n. And the sum of, the sum of a constant times I from I equals 1 to n is n times n plus 1 over 2. So I'm through with the summation notation, but now I have some more stuff to clean up before I take the limit. That's the limit as n goes to infinity. 6 over n times n, that's supposed to be a plus right there. 6 over n times n is just 6. And if I distribute this 27n so that I can write that as a single fraction, it will be 27n squared plus 27n over 2n squared. I'm getting very, very close, but before I take the limit, I want to do one other thing inside this parentheses. I'm going to say, if I break that into two fractions and simplify each fraction, I can see more easily what the limit is. 27n squared divided by 2n squared. The n squareds cancel, and that's just 27 over 2. The second term, this n will cancel one of those n's and leave you 27 over 2n. So finally, we have the limit of 3 terms. 2 of those terms are a constant, and I'm ready to take the limit of 6 plus 27 over 2. Well, the limit of a constant is just the constant. And the limit as n goes to infinity of 27 over 2n. As n going to infinity, 2n is huge. 27 divided by huge, such as 27 divided by 10 billion, is darn close to 0. So all I have left is 6 plus 27 over 2. If I get a common denominator for that, that's 12 halves plus 27 halves is, guess what? 39 halves. Holy cow. We got the same thing using calculus and the limit definition of area as we found when we used our 8th grade geometry. So it looks like the limit definition of area in calculus works. I just hope that I'm not going to have to use it every time I have a calculus problem that says find the area. Turns out I'm not, but that's going to be a lesson for tomorrow.